Good morning to all. Today in this lecture, I'm giving details about simple harmonic motion. So in the last some lectures, we already discussed about periodic motion. So what is meant by a periodic motion? Suppose if a particle moves such that it retraces its path regularly after equal interval of time, such motion we call periodic motion. So there are many examples in our daily life for periodic motion. Earth revolve around the sun because it's repeating 1 year each. So each 1 year it's repeating the same path. So we call it a periodic motion. The moon around the earth also a periodic motion. And a simple pendulum, about simple pendulum, it's also a periodic motion. So any system which retraces its path regularly after equal interval of time, such a motion we call periodic motion. So for any periodic motion, the interval of time to complete one round trip or one cycle, we call a round trip, and also we call cycle of motion, is called period. So what is meant by period means the time taken to complete one cycle for a periodic motion, we call it a period. If a particle in a periodic motion moves back and forth over the same path, such motion or such special kind of periodic motion we can also call vibratory or oscillatory motion. So what I mean by a vibratory motion? Any periodic motion, it's move back and forth over the same path about a fixed point. Such a motion is called vibratory or oscillatory motion. So all periodic motions may not be a oscillatory, but all kind of a vibratory or oscillatory motion should be a periodic motion. So an example for a vibratory motion or oscillatory motion, example we can take the to and fro motion of a pendulum is an example. Vibration of a tuning fork it's a vibratory motion. And mass attached to a spring, it's also execute a vibratory motion. Or in a lattice, the atom, the atom in a lattice for a solid, it's vibrating. So also it's a one kind of a vibratory motion. So the next point is in a motion, the displacement of particle. The displacement maybe it's a for any motion, the displacement of the particle in a periodic motion can always express in terms of sine function or cosine function. So there is a mathematical function sine and cosine. So all in any periodic motion, the displacement of the particle can be expressed as a sine or cosine. So the sine and cosine we also call harmonic functions. So that's why hence the periodic motion often called harmonic motion. So this is some introduction. This all we already discussed in the last session itself. So next we are going to simple harmonic motion. So the simple harmonic motion is a particular type of periodic motion. It's very common in nature. The periodic simple harmonic motion means in this type of motion at any instant the restoring force acting on the particle or acting on it is proportional to the displacement from a fixed point in its path. It always directed towards that point. So what is meant by simple harmonic motion? There is any type of motion in which the restoring force acting on the particle is proportional to the displacement from the fixed points. Such a motion is called simple harmonic motion. In this, it is a very important property is that the restoring force is always directed towards that fixed point. So any kind of system which executes simple harmonic motion, we call it as an harmonic oscillator. So harmonic oscillator means any system which executes a simple harmonic motion, we call it harmonic oscillator. So it is very important. Next point is, suppose I consider a particle of mass m executing a simple harmonic motion. If the particle displacement at an instant t is x, suppose the displacement is x, some instant time t, then the acceleration we know acceleration is equal to second derivative of displacement, so d square x by dt square. So according to simple harmonic motion definition, the restoring force is proportional to the displacement. So F is proportional to displacement, the restoring force F. So the proportionality symbol we can avoid, and F is equal to minus kx. So the k is a proportionality constant. and it's also called Hooke's constant or restoring constant. So where k with the minus indicating for the restoring force always directed towards that fixed point. So the displacement is suppose in positive direction, but it is in opposite direction. So F is equal to ma according to Newton's law. So m is equal to ax equal to d square x by dt square is equal to minus kx, and d square x by dt square equal to minus k by mx. So d square x by dt square plus k by m is equal to 0. If you put a constant omega square, I introduce a constant omega square as a k by m, then this differential equation I can simply written as d square x by dt square plus omega square x is equal to. So very important, this is a second order differential equation for a simple harmonic oscillator. So the next thing is not that much important for you, but you have to understand that while solving this equation, the second order differential equation, we can get the expression for x. X means the expression for displacement. So I introduced here how the solving this equation. I just multiply with this equation with 2 dx by dt. So I can rearrange by multiplying this as a d by dt of dx by dt square plus omega square d by dt of x square is equal to 0. Then I'm integrating once, then it become differentiation will lose. So this x by dt all square plus omega square x square is equal to a, whereas the integration constant, and I need to find what is the value of capital A, and for that I to consider case the x is equal to a, the displacement is become maximum on value where a is a maximum. So it will call later we call amplitude, and we know at the maximum the particle will reach at a point and it will be at rest, and it will back to original position. So that point velocity becomes 0. So while substituting this value in this above equation, become dx by dt becomes 0, omega square x become a. So capital A we can write as omega square x square. Substitute this in the above equation, we can get an expression for dx by dt omega into root of a square minus x square. This is nothing but an expression for the velocity of the particle at any instant. So I am going to integrate once more, and for that I take the variable separable form. Dx, all x term is in left hand, so dx by root of a square minus a square omega into dt. Integrating, it's become nothing but sine inverse form. So sine inverse x by a is equal to omega t plus 5. So expression for x is equal to a sine omega t plus 5. So this is the expression for the displacement of a simple harmonic motion, where x is the displacement at any instant t. A is the amplitude, maximum value of displacement, so I call it an amplitude, and whereas a second integration constant is introduced, that is nothing but a phase constant or initial phase. So this is an expression for displacement of the particles at any instant. So the term omega t plus 5 we call phase of vibration. Suppose the phase constant I consider as another constant delta plus pi by 2. What happened? Please check. There's x is equal to a sine omega t. Instead of phi, I substitute delta plus pi by 2. So it's become sine omega t sine theta plus pi by 2 form. You know sine theta plus pi by 2 is nothing but cos theta. So the expression I can written as a. Sorry, here I am made my mistake here. A cos omega t plus delta. So it means what? A cos omega t plus delta. So whatever the expression we are expressed in a sine, it's same as the cosine function. So that's why previously I have told that the displacement of the simple harmonic motion at any instant can express the sine function or cosine function. Here the both are the expression for sine and cosine, but the difference only in the delta and phi. So this is a phase constant. So suppose we are writing in the sine or cosine only, the phase constant has a different value in two cases. So this is the one point. So the next point I am going to introduce here. Suppose I the t is increased, the time t is increased by a value 2 pi by omega. The function become, so you know value x is equal to sine omega t plus 5. I am adding t changes to t plus 2 pi by omega. So omega is there and t changes to t plus 2 pi by omega. So multiply with omega here, outside an omega is 0, so omega t, omega will comes 2 pi. You know the sine theta plus 2 pi becomes sine theta itself. So in that way this expression is nothing but a sine omega t plus pi. So the displacement after the in time 2 pi by omega, it as the same as the initial value. So this is very important. So the displacement of the particle is same after time 2 pi by omega. That's why the 2 pi omega is a period of motion. I can rest 2 pi by omega as period. So you know omega is equal to what is omega square is equal to k by m. So from that one omega is root k by m, and so that is equal to 2 pi root of m by k. So the number of vibration per second is called frequency of the oscillator. So this is nothing but frequency is equal to 1 over t. So t is equal to 2 pi by omega, that by omega by 2 pi. So its expression 1 by 2 pi root of k by m. You know the f is equal to 2 pi by omega, or omega is equal to, we can return as from that expression 2 pi f. So it's like 2 pi by t. So that's why the previously I introduced a constant omega. That's omega is nothing but a quantity that's corresponding for is called angular frequency. So quantity omega is also called angular frequency. So this about a small introduction. So we have introduced what is periodic motion, what is meant by oscillatory motion, and the second order differential equation for the periodic simple harmonic motion. And later we have solved it, and the expression for the simple harmonic motion is equal to x, displacement expression for the x is equal to a sine omega t plus phi. And later we have found that 2 pi by omega is the corresponding quantity for the time period, and we found that 2 pi f for omega is an angular frequency. So this is all about this lecture. So please go through this one. So read, and thank you.